University of South Florida for my bachelor's and my master's degree. Kind of disparate topics: industrial engineering undergrad and environmental engineering grad school. That lends itself to a lot of systems study, probability and statistics, and then of course cap that with the natural world. It really is a decent entree into stormwater modeling. Before I joined CDM Smith, I was with the Southwest Florida Water Management District, which they have their own split. Every state's got their own TDEC, FDEP, but in Florida they have 5 different water management districts that do flood control, resource projects, water quality sampling, that sort of thing. And my role at CDM Smith currently is a project technical leader, and I live in Nashville, Tennessee. And ordinarily, this is another thing I would put at the end, but there are so many people that I want to acknowledge their work as I go through that I'm given this list of acknowledgements right up top. Because there are several things I'm going to talk about in here that I am not the most eminent expert. I am passing along information that I gathered from these folks, and I want to put their names up there to let you know that I am standing on the shoulders of giants. Might even be a couple of those folks on this call today. So we're gonna figure out a lot of things today. We're gonna ask a lot of questions: why, what, who, and how. Of course, the talk is divided into why. We're gonna talk about the purpose, why you would ever do stormwater modeling, kind of what it is in theory, the process, the weedier part, what gets done, who does it, how to do it, and then at the end we're gonna talk a little bit about products, which is not necessarily the software that you would use, but what results you get and what to do with those results from stormwater modeling. We're going to mostly be talking about water quantity, but I have a couple of slides about water quality up front because I know that we're very concerned with water quality in this state and as MS4s. We're going to talk about who does stormwater modeling, who should do stormwater modeling. Is it the staff that you have on hand? Is it a consultant? Is it a university? All three, and depending on your program, could do stormwater modeling for you. And then the how. I have the dollar signs and the question marks there. So the main sections here, I have epigrams from a man by the name of Michael Sorkin, who is a famous architect who wrote this sort of almost like a poem where it's 250 things every architect should know, and one of them is hydrology is destiny. And I put him down there because unfortunately in April he died of COVID-19, and I had not been acquainted with him until then, until somebody wrote a very touching thing about him. But hydrology is destiny. Keep that poetic thing in mind as we dive into this. And here are some more questions. This is kind of another layout slide here. First, we know what are we trying to solve? What problems are out there that stormwater modeling might be the solution to? Where are we at as an MS4 program or as your program for your entire city? Are we ready to do that sort of thing? Should we model this part of the system or that part of the system? Should we model this system in italics there? Can we do this? Are we ready to do it? And then later on, we'll talk about how do I know that this model that we or somebody else has built is any good? And do we want to own the model, or do we want to just look at its output? So that's some of the stuff that we're going to be talking about over the next, I don't know, hour-ish here. What problems are we attempting to solve? Stormwater modeling could solve a lot of problems. It could also introduce new problems that you didn't know that you have. Oftentimes, you know maybe where your repetitive loss properties are. You know what you would like to fund via different mechanisms as a capital infrastructure program project. Is there a particularly sensitive area that kind of goes along with that repetitive loss? Are you doing a master plan? Are we tackling entire parts of the city to look at those repetitive loss areas? Or are we just doing this sort of thing to verify that we don't know what's going on in the system at all, and we're trying to get our head around where our city's at? These are all valid problems that you would want to solve with stormwater modeling. And as I said, we're going to talk a little bit about water quality and water quantity up front, because the mechanisms for modeling those two are very different. And these check marks here are pretty generalized, but they hold true somewhat for what I'm going to be talking about water quantity wise. Because when we talk about water quality, we're generally looking at these point source things or non-point source things, where we're very concerned with how outlets and outfalls behave. And in water quantity, we need to know about the entire river that outfall or that non-point source, point source stuff is going into. We need to know the entire basin, so we want to know about how the entire system behaves. And in water quality, oftentimes we're talking about unusual site conditions. We're talking about construction. We're talking about SCMs that may or may not be maintained, or accumulations of dog poop or something like that. Whereas in water quantity, we want to get like the average picture of the site. We want to know when that storm comes. If everything was going right, what's the situation? In water quality, we're concerned a little more with human activities like pesticide or fertilizer use, whereas in water quantity, we're looking more at how mankind has impacted his environment structurally, the impacts of impervious area and so forth. And then in water quality, we're talking about TMDLs. We're looking at long-term continuous loading. Whereas in water quantity, you want the worst hour of a 10-year period. You want to know that system completely under stress, because otherwise your system's probably designed to take, first inch, whatever else, the stuff it's going to see regularly is really of not much concern to water quantity. And a little more heady on the end of it, water quality tends to be a little bit more deterministic, whereas it's about repetitive behaviors. If we do this, then that happens. Whereas water quantity, that stuff will happen. We're looking at the probability when that big storm hits, what happens. And so with water quality, on the right here, I have that's Gayoso Bayou in downtown Memphis there, a really intricate palette of land use there. And so in that area, you have all kinds of different point source versus non-point sources. And when you're talking about water quality, generally you're concerned with the first flush, how long has it been since the previous rain, not necessarily how much rain there is. It can be very assumption intensive about how many people in your city are spreading fertilizer, or like who the bad apples are with a point source discharge. And I forget exactly which paper that I read this in, but pathogens, specifically E. coli, often exhibit what they call extreme spatial variability. So to say that this general spot here, this dog park, always has this amount of runoff, even then the amount of E. coli in that still could be very highly spatially variable. But you can approximate this stuff pretty healthily by land use, and try to look at it from a load reduction standpoint over the course of years. And there's a great model for doing so. It's just a spreadsheet model with a bunch of checkboxes and macros. It's pretty nifty. It's called the watershed treatment model. And you can tell this thing, okay, we're doing this amount of riparian buffers, or we have this many marinas in the city, and this is the makeup of the land use in the area, and it'll kind of run the numbers and give you a generalized load reduction. But it's not dynamic. You're not looking at something where it's feeding runoff into a pipe or a channel, and that channel feeds to the next one or anything like that. It's just doing algebra essentially instead of calculus. So with water quantity, which is what I'm mostly going to be talking about today, these are the big scary events that we're trying to protect. Major loss, the loss of life and the loss of property. And they're the things that you may not have ever seen before. And this quote comes from my colleague Adam Reeder. It was very succinct and beautiful, that our context for flooding is, it's behind my icon. Our context for flooding is often only as bad as the most recent flooding. So even if there were worse flooding maybe 20 years ago, you're still thinking about the one that happened 4 or 5 years ago. You have watermarks from that. People recollect it. And the picture here is from Hurricane Harvey. Obviously, that's an extreme event, but no one could have probably foreseen this degree of inundation in the area. So we'll be talking about CIP planning for whether or not we do detention, retention, how to size culverts. That's what we're looking at, is big time structural long-term impacts on basins that we can glean from water quantity. Before we even undertake this idea of whether we're gonna try to CIP phase something like that, it really helps to know where you're at as a program. And we have the level of service here on the left. We've used this, folks in Gallatin, we probably showed this to 1 million times. Sometimes we use 1 through 5 if people don't like the idea that they're getting a D. But the truth is that most programs that are out there are probably in that C to D. Like nobody's really failing. You're in big trouble if you're failing. But nobody's really getting the A either. The A is very costly. So, you know, most cities are probably responding mostly to calls. They might have a good idea of where the repetitive loss areas are, but it's reactionary. It's primarily reactionary. Critical needs are getting improved, but there's not this phased implementation of big time projects. And whether that's a lack of funding or staff time, it's often all kinds of stuff. But where we start to see the stormwater modeling horizon come in is as you pass into that C to B, where you're doing proactive planning and trying to decide on where your phased implementation is. That difference between being reactive and being proactive is where stormwater modeling comes into play. And we'll look at this again later. And as part of that, looking at operations and maintenance and where your program's at, where are we as a infrastructure existence, or where do we know where things are at? Asset management is really, really important. I am not really an expert in this sort of thing, and I believe that the next TNSA talk talks about asset management, but it's just so critical that you're not going to be able to build an incredible all-knowing model without a really robust asset management plan. It's the foundation of everything else. Because once you have that inventory and that condition assessment in, then you can start to evaluate the risk to those things and start to apply a good high quality model to that high quality data below. And part of the questions that you may ask yourself as you assume, is our asset management ready or not for stormwater modeling? Are all the departments talking to one another? Do we have the same picture of all of our stuff? You know, does parks and public works and engineering and stormwater, are we all looking at the same thing? Is GIS up to date for all of this? You know, it really, asset management is everybody's onus. And then so as you get that in line and you start to think about what we're going to be modeling out there, there are some, I would say, rules of thumb to maybe where stormwater modeling is what you ought to do. And I got Jeff Goldblum down there. You know, you're so preoccupied whether or not you could. You were excited to do it. You didn't stop and think if you should. You know, and I have some examples here. A 500-acre neighborhood with repetitive flooding that you are saving money to work on, absolutely model that basin. You know, and spend a lot of time on that area where you know that there's flooding and you think that you can spend the right amount of money to get it under control. And there's a lot of debate about the second bullet point, a citywide system of all pipes and inlets. In some cities, they really do model absolutely everything. I think that's probably unrealistic. But it's possible. Your asset management may have the inverts for everything, but when you're looking at, you know, hundreds of acres and where stuff's interfacing with streams, do we really need to know all that information about the city? Probably not. You're probably cutting things down to 24 inches or larger. A small system with drainage issues that are known to be related to maintenance, that's probably not going to get its own model. A pipe or box culvert upgrade project that you're looking at trying to size the pipe maybe, yeah, sure. You know, you could build a small model to do that. Or in theory, you know, if you've already done that 500-acre neighborhood, or, you know, you've master planned entire basins, then you can use those models to craft the improvements based on their output. And of course, an area slated for significant future development, building a future stormwater model would be very helpful too, almost regardless of size. It's really interesting to see how impervious area changes runoff. Should we model this system where, you know, another hint could be a heat map made from your work orders. And this goes back to some of your asset management. Are your work orders geo-referenced? You know, oftentimes when people go out and they have survey 123 or an Excel sheet that you're doing, you know, you write down maybe like 200 First Street, but that's not really a point that we can mix into the GIS and create a heat map. So thinking about how you record your asset management for other purposes is important. And it's impossible to know every manifestation of what your data that you're taking in the field is going to have in the future. But knowing beforehand that that something like this would be extremely useful for reading stormwater modeling output helps. Or you can always have an intern read the address and make a point there, which is, we've done that before. It's great intern work. And should we model this system? You know, that's a frequent question, because it's obviously, you know, sometimes you get a little sticker shock from a university or a consultant about how much something might cost. And you think, we're experts, you know, we have this. And you absolutely are experts. And you know more about your system than any consultant like me is going to walk into this city. I don't know the ins and outs of every basin in Memphis. There's no way I could. But it's a question of how robust is your GIS department? You know, are they on board with this? Are they going to be able to supply you all the data? How much time do you have? It's very time intensive. It can take, you know, hundreds of hours. How much uninterrupted time do you have? Because this is really kind of deep work, where when you dig into the hood, it's not something you graze at and you do for 5 minutes and put aside. You know, there need to be devoted hours at a time when you can fulfill a task and go through point by point and make sure that everything's high quality. And then, of course, who can independently check and verify? For the project that we're working on in Memphis, I've showed you a couple of screenshots from Christian Brothers University. Has a hydrologist that's independently verifying everybody's work, and that's the right way to do it. Because otherwise, somebody hands something in, and you don't really know if it was really what it was up to be or not. Because maybe you don't have enough time to dig through that, or time or expertise to dig through that model and know whether or not it was what you asked for. So getting somebody to check your work or the work of others is really key. Epigram 2 from Michael Sorkin is, creation is a patient search. Very beautiful way of thinking about how creation is a lot of head scratching, really. And we're going to be hitting these four points here as we go through some colloquialisms for you. Garbage in, garbage out, all's well that ends well, gilding the lily, and using a shotgun to kill a fly. So talking about that asset management stuff, here's a real laundry list of stuff that's useful when you decide to take the plunge and do stormwater modeling. You need rim inverts, manhole depths, head walls. It's very survey intensive. You need pipe and culvert diameters. The LiDAR can help fill in some of it. Land use and soils coverage, that stuff's easier to get. Stream cross sections may require survey. The georeference complaints that I talked about. Ideally, you would want to have some flow monitoring too. If you've got a smaller creek that doesn't have a USGS gauge on it, or if you're looking at a very large box culvert that you want to know how the stage and flow is related there, you would want to put some flow monitoring in, and do so in an advantageous time of year to catch a large storm event, you know, and that depends greatly on what part of the state or the country you're in. Generally, we would say sometime in the late fall through spring would be a great time. And ideally, you put something in for an entire year and try to catch a large event. And then rainfall monitoring, you know, the airport's good, but ideally you put a few gauges out to try to get 5-minute data, get really, really precise granular data. And then for verifying the model and knowing where impacts could be, you would want high water marks or BFEs. And that creation is a patient search. You know, it could be 500 plus hours of staff time to develop a really robust model, depending on what basin you've selected and how hairy the data can be. It requires an extraordinary amount of patience. And then as a segue to the next slides here, software selection and license. You want to make sure that you're using the right platform to get the right answers for whatever basin you have. So here's some data sources for some of the stuff that was just displayed. NOAA Atlas 14 will kick out intensity, duration, and frequency curves for almost any point in the country that you'd like. It's really amazing. I just recently learned about this USGS SW toolbox, where, you know, any gauge that they've got in their repertoire, you can pull the data down and perform these almost one-click calculations. Like I have a screenshot of the 7Q10. That's the lowest 7-day sustained flow in any given 10-year period in a basin. And, you know, you click that and it has it right there. It's really something. Of course, your in-house monitoring, the property assessor, you know, you can use parcel data to understand land use. Maybe the county has a lot of data that you don't have. I know that Shelby County has a lot of data that Memphis doesn't. And then, of course, TDOT has plans for road crossings, and there's a lot of stuff out there. It's just that you got to do some of that patient searching and sleuthing to find out if that data is available to you and if it's useful. So moving on to the major modeling platforms that we're talking about. There are several, and I'm not going to talk about every single one. They're kind of like the big three that I'm going to cover. And the first is HEC-RAS, and that's probably the one that that most people are probably at least familiar with, because FEMA utilizes it. The Army Corps utilizes it. It's how LOMARs and CLOMARs are done. It's cross-section driven. They look at bridge crossings and culverts. It's not traditionally used for like an urban or suburban development. We're talking about large-scale rivers and creeks, and then it's moderately survey intensive. You know, you want to get a decent bathymetry of the channel where you can, but realistically, you don't have to get all these manhole inverts and things like you would for a different platform. I am not an expert in HEC-RAS. I have to say I've only used it just a couple of times to make very basic models, but I know that it's extremely powerful and it punches above its weight in reputation. And I think that I bolded that first line on purpose because it is free. That's very important too, because some of these other ones that we're going to talk about after this are not free. The modeling platform that I use day in, day out is EPA SWIM. Right now they're on 5.1.14, I think, just came out. The upper right there, that black and white one, is what the SWIM interface looks like. It is relatively archaic. It is not particularly user-friendly. It's free, but it doesn't really pair with GIS. You're looking at data that is being displayed from a text file. So it can absolutely feel like you're back in the 80s writing like Fortran or something like that. There's a lot of room for error with it. So there are these other two major programs that have taken the SWIM engine and the SWIM mechanics and built a really nifty graphical user interface for it. And the one I prefer is PC SWIM. It's out of Canada, CHI, the Canadian Hydrologic Institute. And what it does is that automatically when you open any SWIM file, it makes shape files for you in GIS so that you can edit there and it brings them back and forth. It's a much cleaner look. You see this model from Virginia Beach here. It's extremely detailed, and my head hurts looking at this. I couldn't imagine how bad it would look in free EPA SWIM. It has a large toolbox of features. If you put a DEM in, it will squeeze out catchments of a certain refined size for you in a matter of minutes. It will set losses. It does all the weedy stuff for you so that, you know, it can do 80% of the work quickly, and then you spend 80% of your time making sure that all that work was any good, but at least it's a little less tedious with some of these toolboxes. And InfoSwim does the same thing too. It's a more customizable interface. It looks like GIS. When you pull it in, it is literally like the ArcMap look, and has a lot of the same features. It probably has superior flood mapping capabilities to PC SWIM, and both of those are a few $100 a year, 800 and 560. But as you get into SWIM, it's going to take a lot more survey to get a meaningful model than it may be for HEC-RAS, because you're talking about inlets and culverts and cross sections on a degree of terrain and deranged areas and developed areas that you didn't have to talk about with HEC-RAS. And the third one I'm going to talk about is my buddy Mike Urban, which is actually a really incredible program. I've used it a lot for collection systems modeling, the sewer system modeling. It's extremely good at that. It valving and pumping is its forte. It has a really great scenario manager so that you have just one model with all these things you know, check on or off. I would say it's very difficult to use. It has a lot of quirks that can really mess you up. And as I know Carissa's on this call, Carissa and I found out that the Mike Urban 2017 actually had a bug in it that made it completely useless for stormwater features. The cross sections were coming in and the X and Y was swapped, and there was no way to fix it. That's just mind-boggling that it was that way, and they fixed it in 2019, but it doesn't give me a ton of faith that their SWIM engine and their capabilities of modeling are any better than the PC SWIM numbers are. And I bolded this one too because it's $3,000 a year. So that's something that when you think about, do you want to be able to own and operate a model that a consultant delivers for you or that you develop yourselves? Do we want to pay $3,000 a year for a license for this in perpetuity? Nashville, City of Nashville Overflow Abatement Program decided that they didn't. And 2017 was the last year we delivered models in microurban format, and we swapped to swim because it was free, and they were spending thousands of dollars a year to not really look at the models. So knowing that those are the platforms, and you're going in, you got all your data, now you try to figure out, what storms we're going to model. What is our level of service? Where was our level of service now, and where do we think we can get with these questions that we're asking the model? Are we looking at all the large pipes in this system? Do we want to add detail in certain areas that we know are sensitive? Do we make that assumption that I talked about before, where all inlets are operating properly, but do we assume that there's a heavy amount of losses in certain areas, or that things are not the usual site conditions? What do other organizations use? I think the 24-inch and above is kind of a rule of thumb, but that's certainly not what every state and city uses. What can we afford to do? That's kind of the really important question there. Obviously, in theory, if this was an inexpensive exercise, we'd model the entire city, every inlet, every storm event, 100-year storm, you name it. We would look at all those things, but realistically, we have to be a little smarter than that to afford money-wise, but afford time-wise too, because I said this takes hundreds of hours, and there's a lot of review involved and second guessing. What can we afford to get done expeditiously and maximize benefit and cost? And that last one there, what can we not afford to ignore? That's a little more philosophical, but what is the most pressing thing in our city? And level of service can be very squirrely. You have diminishing returns oftentimes for your higher return period events. So if you model the 5-year storm and the 100-year storm, there's going to be a lot more structures and roads and stuff that are inundated. But if you model the 10-year storm, and the same things are inundated, but they're 1 foot deep in the 10-year and 3 foot deep in the 100-year, you're not getting the right criteria for benefit cost there out of that. And choosing the right return period of event that's somewhere in that Goldilocks zone will help prevent the sticker shock of the solutions as well, because trying to corral a 100-year storm is honestly pretty inadvisable and unrealistic. But if you can find out that maybe some areas you're going to get 100-year storm benefits with a 10-year storm improvement, that's nice to know as well. I have this big chart over here on the right that this is February of 2019 in Nashville, and this was a 60-day period. And rainfall is obviously very organic, and the word aleatoric, I guess, gets thrown around. But if you just looked at the most intense 60-minute period, the most intense hour during these entire 2 months, you only had a 2-year storm. But if you look at the most intense 6-hour period, it's a 200-year storm. But if you jumped from a 2-hour to a 24-hour, maybe it's only a 50-year storm. So it has all these different criteria where there's this intensity that that's particularly crazy. If it rained, like the most crazy 5-minute intensity, but it's way less than an inch, do we plan for that sort of thing? Or do we try to look at a 24-hour, what's going on in a day? Because as you see, as we get out to 20 days, there was another reasonably large storm somewhere between 10 and 20 days that put them back up to a 200-year recurrence interval in a single month. They had almost 16 inches of rain in February of 2019. And that's hard to plan for, but if you'd only looked at one of these certain things, you only looked at the 24-hour, you may not get the whole picture of what the intensity was, and thus what the impacts were to the system. And here's a way of, I have several of these slides we'll go through pretty quickly here, of kind of imagining the way that the model thinks, and look at this and think about if this is the way that you can pivot your understanding of objects into the kind of cold robot style of these models. They got rainfall on the left, but it ends up being essentially a bar chart with these volumes and intensities on the right. And you may have something that looks like we have on the right there, where you got a foot or so of water across this cross section that means nothing. You think, okay, a foot of water or so. What it really probably looks like is this street over here on the right, and then the sidewalk's got an inch or two of water in it. Sidewalks up here, maybe you have a little bit of curb, but the street's got a foot of water in it. So your context for what this block looks like it should be firmly rooted in the real life. And then, you know, you look at a neighborhood and you can distill that neighborhood down into pervious and impervious area, and then the impervious area into which impervious area runs directly into inlets and which of it runs across yards and other pervious area. And you know, it gets pretty weedy when you look at that, because each of those has different factors that help know how much runs off, how quickly it runs off, and where it runs off to. We got our old castle box culvert drop structure over there on the left. What that looks like in the model is actually a line feature between 2 points, and it has relatively similar dimensions. It's a bottom orifice is the way it's put in there, a rectangular closed orifice that has a discharge coefficient of, I don't know, 0.62, maybe it's as high as 0.7. But, you know, we're used to seeing these sorts of things all the time, just sitting out there in the middle of a basin or whatever else. But you know, they have all this math that's written on them that the model will use to find its discharge. So say you've built this entire model where all your bottom orifices are lines and all your manholes are in there and all your stream cross sections are in there. How do we know if it's any good? You can look at the continuity error, which is some basic math about what went in and what went out. If a lot more flow went in than ever went out, and it missed something, that's not a good sign. If more flow went out than went in, that can happen too, and that's not a good sign that your model's any good. There's this thing called glass walling that we usually look for. If you look at that transect over there, you see that one side of this model has a nice sumptuous floodplain over here on the left, but you know, unless there's some sort of like seawall or something right here, I feel like this other side is not being represented properly, and it's probably boosting the level in this creek artificially. And colloquially, that's called glass walling, and that's generally a sign that your levels might be off and that you need to try to expand this cross section as best you can. No internal time series. I'll tell a very brief story, and I will not tell you where this happened, but I it was not in the state of Tennessee, but I was tasked with reviewing a model, and it was for permitting a bank or something like that, and they wanted to disturb wetlands with this bank that they were building, and they submitted a model for it. And what was coming out was nice and pretty, but it did not seem to be possible for the storm event that was going in. And when we looked under the hood, the very last element before the outlet was just a time series. So it was like fabricated results coming out of the very last pipe. And you know, I kind of sat back in my chair and thought, oh, this is fraud. This is negligent. You know, I'd never seen anything that egregious, never have since. But you know, it's worth your due diligence to look for odd things like, why is there a time series at the last pipe? You know, why it's that should all be dynamic going through there. You know, do you have if you have a pipe system, do you have overland flows too? So that, you know, in a stormwater model, not everything goes into the pipes. You know, when those pipes get full, it's running down the street. It should be running down the street in the model too. Are they using values that are close to literature values? You know, Manning's in makes a big difference. You know, if you have a Manning's in that's like twice what it should be, that's almost physically impossible, right? There's not a lot of wiggle room on certain factors. Even if your model is not accurately predicting what you've got, there's only so far you can turn some of those knobs without getting outside the boundaries of reality. Is that a question? Let me see. I actually got a thing. Accurate as-built. Yeah, Don is 100% right. Oh my gosh, how many times have I pulled up as-built, you know, from like the 70s, and you know, I have a microscope essentially on these things. But then I remember, oh, if it's from the 70s, it's an NGVD and not NAVD. So, you know, what's our factor here? Do we need to adjust this by 0.8 feet or something else? And I write this too, and this is kind of like maybe shooting myself in the foot. Beware the fancy graphics, you know, because oftentimes things look really awesome. They like some animated results and like these really sumptuous looking things, but garbage in, garbage out. If, you know, the animated graphics have glass walls in them, and you know, the pipe inverts aren't right, you have inverse slopes and things like that, it doesn't matter how good it looks, it's not right. How do we make sure we have a useful model too? Because the good model being very accurate and sound isn't necessarily a useful model either. And that's part of what your level of service is. You know, if you want to say, we're going to try to mitigate the 10-year storm, that should be what the model is planned for. Is, you know, is there appropriate level of detail? I know the big joke on CDM Smith was CDM is always cost don't matter, right? We're notorious for gilding the lily and putting all this detail and having all this pride, but it's like, just get it in there. Like, do we need 3 decimal points on all this stuff? You know, where's the model sensitive to? You know, at what point does turning that knob not make any difference? So ideally, the model should be tuned to the proper sensitivity. And on the next slide, I'm going to talk about the difference between calibration and validation. And there's two different things, and it's something that you should maybe talk about in your scope, so that you can have a calibrated model where everything is properly tuned, that the estimation and adjustment of the model parameters and constants are in agreement between the model and data set. So this is actually a sewer model here, but that's a pretty tight, green being the observed and red being the model. That's a pretty tight agreement between the two. But is it consistent with the intended application of the model? Can we find a little? Is there more wiggle room in there to get the high watermarks that we see in the street? Because just because we have this monitor correct doesn't necessarily mean that it's matching any of something else somewhere else. So is it valid standing on top of the calibration? I know that this is highly semantic, and there's verification too, but are we within a satisfactory range of accuracy? What can we live with the validation, as long as we're, is there flooding where we're seeing a lot of calls? That's just as important as having a tight line on top of the other line. And do we want to own this model? What do we want to do with it after we've verified it? We've got the plans. Are we going to keep working on this? Who's going to keep working on it? When do we do it? Do we shelve it? I have this long list of frequency updates. I know that I've worked with City of Virginia Beach a lot. Those guys, they dig straight into those models frequently, because they update it with like the NOAA sea rise forecasts, and they're still getting survey even after we deliver this plan. Survey keeps coming in, and new BMPs keep getting built, new SCMs keep getting built. That stuff should go into the model for your next round of revisions and for your next round of CIP planning. You don't want to keep planning for 2020 when it's 25 and you've already built a bunch of stuff. So do you want to do that, or do you want to have university updated or consultant updated? That's something to think about. So once we've done all that, we have some products. It is possible to begin designing anywhere. This is a nifty graphic from my colleague Elias Gruber, where they have a flood mapping tool in GIS, where you stick in this rain on top of the DEM rather, and they have all these locations where they compare flows, and it'll squeeze out very nice looking products just like this, where you can underlie any. It's getting a little crazy in my house. I don't know if you can hear my 2-year-old, but anything you want under it to help tell the story about what your floodplain issues are, your base floor elevations and your existing floodplains. How tight that 2D grid mesh is depends on your level of service. It's probably unrealistic to have a 2D grid mesh for this entire basin, but if you have an area where you have seen in a coarser model that there are issues, you could always add a mesh in a very specific neighborhood or floodplain to try to get that accuracy later after you've looked at the entire system. That precision is probably the better word. This, to the keen eye, is New Orleans. That's the Garden District of New Orleans. Have we validated it with observed conditions? Are we seeing water out there that's that deep, and with what frequency? And flood mapping, when you look at it in a total sense like this, really helps your expectations management. You see a photo like this and you think, oh boy, okay, what do we do? What do we do first? Or like, what can we even do? Like, mitigate your fervor. But it also helps to realize what is the absolute worst thing, and where do we start on top of this big pile of things. Maybe it's this Southwest Career and Technical School that is completely inaccessible in a flood. Maybe we can start there. But staying in New Orleans, this is an example of a project where they knew that they had those sorts of issues, and they wanted to do something a little bit more holistic. And the city was very keen on utilizing green infrastructure too. And so they killed several birds with a couple stones. A stone thrown by HMG GP, which is the Hazard Mitigation Grant Program. We'll talk about that a little bit more later. But there's a very exaggerated slope to understand here that there weren't a lot of really great flow paths for this flooding coming down the hill into Lake Pontchartrain. It was coming through neighborhoods and across these streets. And so their idea was to improve each one of these streets to be a terrace that collected and detained water. And so we'd like to think about something like a stormwater lot or these little detention basins with bioretention as being something that removes certain pollutants, but they have a water quantity impact as well. So you can build water quality into the back end a lot of your water quantity concerns too. And then these renderings also help with traffic calming and walkability and general joie de vivre of the neighborhood. So this is what it would look like before without all these massively distributed green infrastructure locations. So using the model to look at how green infrastructure impacts it, and then it's a decent impact, at least in the worst areas. But part of that was defining their level of service. Were they willing to have under 6 inches of water in a roadway? Yeah, probably. But then when you get to up to a foot or a foot and a half, that's when the location of these things was sussed out. This is our buddy. I forget the name of this. I don't know if Brittany's on the call. We did a cleanup on this place in Franklin just in the fall. This is Mallory Lane and Franklin Road. This was a detention project, but there's also educational signage. There's a path here to help people learn about stormwater and the effects of uptake in the pond. So when you're thinking about these things, you're not just making the water go away. They can possibly be public features for you too. So this is stuff that when you cite it, and you're thinking about, well, this is where the impacts are. There's a lot of room for creativity. Your design can begin with something that's dire and end with something very beautiful. This is Mark Zito's illustration. We want to know how much should we do, where do we do it, and when. When is very important too. So if we want to try to figure out which one of these is the most important thing to do, because it's never quite as clear as like, this area is absolutely the worst and we know it. If that was the case, then we wouldn't even be talking about this. Oftentimes there's immense pros and cons for every potential project derived from stormwater modeling. So you want to try to derive tangible, oftentimes costs that are could be derived from this project. So you want to try to mitigate loss of property, loss of life, loss of resources. Oftentimes as we prepare a basin modeling report, we'll list the key facilities in that basin: schools, roads, major roads, fire departments, so that we know that there aren't, in a certain storm event, there's not flooding that prevents a fire truck from leaving its bay. And then from knowing where those losses are being mitigated, how frequently are they being mitigated? So if it's every 10 years, it's not helpful to think about that as 10 years from now. A 10-year storm could happen tomorrow. So it's better to think of them as an annualized loss exposure, whereas every year you have your 1-year storm losses, your 2-year storm losses, your 100-year storm losses that are decremented at the right potentiality of them occurring. And that's what the FEMA's benefit cost analysis tool does in a nutshell. And once again, I'm not an expert on this. There's a whole presentation to be given on this, but I'll run through it super briefly, and then I'll talk about the decision support tool. Or I guess I'm talking about the decision support tool first. So this is the one that we built for Minot, North Dakota, which sees these large, like catastrophic flooding events that seem to be occurring more frequently, but they're heavily snowmelt driven. And they start in Canada, they come down through North Dakota. So the idea was that we have these existing models and we know that they're verified, but so what do we do with these models to try to figure out the most expeditious improvements for them? Is it dam operations? Is it buying out all the flood options? So there's a thing called the Stella model, which is a prioritization tool effectively. And you could have up to hundreds of different scenarios where it's like, do this one, do number 1 and 18, or do number 19 and 15. and crunch those numbers to figure out where the best benefit cost is, then go back to the models with those dam operations or those criteria, run the model again, rerun Stella and say, is this really the optimized thing in the hydraulic model with the benefit cost? And then the verification is in, you know, the hydrographs that we get out, whether or not we want to buy out homes, you know, where the money then goes. And that is dictated by the benefit cost analysis. I know this is so complex that, you know. Okay. FEMA's BCA tool is really nifty. You have, it can be used for almost anything up to like generators for when the power is out. I've worked on a BCA project for wildfires in Colorado. It's not just flooding, it's just about how often there are catastrophic impacts based on a certain recurrence interval. Wildfires have recurrence intervals like floods do. So if you know a bit about the cost, if you know your buyout for this location, you can place that project in there like a buyout, or let's not do a buyout. Let's talk about a potential project that you're putting in. If it's $1 million project and you expect the useful life to be 50 years, you know, how much is it going to cost to do it each year? But then that gets compared to what the potential damages are. So if we know that there were damages in 2010, 2013, 2016, we know that the damage is frequent enough that over the lifetime of 50 years, there's probably going to be a really good benefit cost on this. So knowing your historic damages and knowing as much as you can about high water marks and BFE elevations in your community can really help you prepare a benefit cost analysis to try to gain funds from the hazard mitigation grant program. And you know, modeling can help turn an uncertain future where you have these projects that have been on the books for a while and there's some devoted funding for them, maybe you don't even know, into something where you have a number for the loss mitigation. You know the vulnerability score of the area now a little bit better, and you can try to phase those things. And I have, you know, study identified phase 1 projects. Maybe these were all the ones that were 4 and 5, and you're devoting 50,000 to 100,000 a year to work on those. And put plainly, it helps to demonstrate that, you know, it helps to demonstrate that reducing flooding at the ball fields also prevents the fire station. I know we all want to get the ball fields cleaned up, but you know, if you can look at the bigger picture and get into those areas that are big on the benefit cost analysis, that helps out. So what does this cost? There's really no rule of thumb. You know, it could be up to $200,000 a square mile. It really depends on what kind of survey you have to do in the basin, stakeholders in the basin that may slow things down or speed things up, what the basin looks like, you know, and the questions we're asking. You know, are we using a shotgun to kill a fly here? Are we overdoing it? To buyer bewares here, it may end up costing more to do less. So if you're just picking at things over and over again, sometimes pulling the Band-Aid off and understanding the basin and prioritizing things ends up saving you a lot of staff time and a lot of headaches. But then, buyer beware number 2, it may end up costing more to do more. You know, if you just select this basin because it's an easy one to do or something like that, you may end up with very few projects or very little benefit cost out of it. But you can always use, I'm running out of time here, so I'm going to plow through stormwater utility fees. Like I said, that's a whole other talk. That's a commonly used one to try to build up your coffers for CIPs. There's bond programs. Vina Jones talked back in March about state revolving funds, which there's money out there, go get it. I think the key takeaway from this slide is that the American Society of Civil Engineers is grading stormwater next year for the very first time, right along with roads and buildings and the stuff that they usually look at. Oh yeah, I forgot about polls. Yeah, forget the polls. Well, one of the, you put up the first poll. The first poll is where do you think your program is on that A to F scale currently? You know, are you just keeping your head above water, or you know, are you proactively planning for CIPs? Is your operations and maintenance on a very rigorous schedule, or is it mostly reactive? And then so looking a little bit ahead, you know, where are we going to be what are we going to be talking about in 10 or 15 years with stormwater modeling? we'll be talking about really awesome asset management, getting to that A in asset management, you know, where you have drones flying LiDAR for you and drone related inspections, augmented reality in the field, you know, using iPads to collect data, but not only that, collecting really high quality data. You could have something like the integrated water analytics here, where a project that I worked on in Australia was a flooding issue where they would take the Doppler forecast ahead of you, and they would run that through the model that we built for this. So 50% C, yeah, this breakdown is almost exactly, like nobody's failing, but you know, there's probably only a couple of us that are really in a B or in an A, and it has no bearing on how big your city is or where your city is. It's unique to every city. I would say that's totally what I would have thought. And with the Queensland project in Australia, so they had this radar rainfall that they would forecast hours ahead of time, and it would give the stages at a certain point. And what the tool would do is, if it got to a certain stage in the model, it would pop up all the paperwork that you needed to do something like close a road or order sandbags. It streamlined all the bureaucracy around disaster prep for you based on radar rainfall. And like the worst thing happens is it dries up and you don't get the flood, but you ordered sandbags or something like that, or you at least did the paperwork for it. But that was something that I really really opened my eyes to the actual applications of this stuff. Future trends here in the Southeast: increased frequency of storms and you know, changes to seasonal precipitation. You know, with climate change, everyone likes to talk about the, you know, sea level rise and more frequent storms, but out west it's probably more frequent droughts. Everybody's got a different possibility according to the third national climate assessment here. And we talked about this, I believe, last year at one of our quarterly meetings, but you know, I think that Nashville or Middle Tennessee's had several high recurrence interval period or rainstorms come up in the past few years, and you know, it just feels like you get 3 5-year storms in a row, and you're like, well, what even is a 5-year storm? I don't think that's true anymore, you know. And that's somewhat supported by literature that I read published in July of 2019. Is that study from Wisconsin and Carnegie Mellon has claimed that um, much of existing and planned hydrologic infrastructure in the United States, based on published rainfall design standards, is and will continue to underperform its intended reliability due to these rainfall changes. And they very diplomatically recommend continued discussion. So here's a little of that continued discussion. City of Chapel Hill, North Carolina, asked a colleague of mine to look at that sort of thing and say, you know, we have all this data going back to 1978. Are we seeing more frequent storms? Like, where is the target moving a little bit on what a 5 or 10-year storm is? And they showed a fairly tight agreement that if you had done an IDF analysis in 1998, you would probably have a different volume than you would in 2018. But it's still probability based, and this PN formula here is still holds up no matter what the volume is below it. Because here is the data that I recently pulled for Memphis, and you know, if you can make a trend out of that, you know, let's talk about it. But it's, you know, it's hairy. You know, the climate is a very hairy thing to try to figure out. But there are global climate models out there kicking out output for a variety of different future simulations. And my colleagues Mark Mamoni and Sebastian Malter published results in June 2019 of a study that they did for Philadelphia, where they were taking those existing 10-year storms and stochastically combining them with these future volumes to try to get something that approximates what a storm in 2070 would be. Because the global climate model output is, I think it's only daily rain. So it may say 6 inches, but you know, is that a drizzle all day long, or is it, you know, a 6 hour in a 10 or 6 inches in a 2-hour period? It's a really cool article. I urge you to read it. I am totally out of time, and I've reached the end of my presentation here. But hopefully, in that long rattle of things that I've just told you, we came to some sort of understanding of where stormwater modeling fits into your programs, into trying to prove that things that you're doing in your communities are worth the funds that your department has, and how to point your program at doing stormwater modeling in the future. It could be years ahead. But any questions? I'm open. I see a chat just come through. What stormwater modeling program is good for sinkhole flooding? Right. So if you do have a karst environment, I have worked with two. In Florida, they have a lot of karst environment too, and you can use swim for that. It takes some interesting thinking though, because swim has the ability to handle aquifers, and it understands aquifer recharge, and you put in all this information about it if you choose to do so. But with a sinkhole, that's not really aquifer recharge. It's ripping down in there, you know. And there you can model it as a pump, or as a feature that goes down into the sinkholes. But there's also a program called ICPR, which I didn't really talk about. It's interconnected pond routing. It's relatively basic, but so it's like a bunch of boxes that line up next to one another. And in one of those ponds, you can have, you know, an extraordinarily rapid recharge within that pond. With the sinkhole, that's not something that I don't know. Think about it. It'd be very useful in calibration. You know, when you're thinking about a storm event or flooding, it might be negligible, the amount that goes down into it. But I would still say that that's probably swim. It's not going to be HEC-RAS. But swim has creative ways to deal with handling deranged terrain, or endorheic terrain, where stuff doesn't necessarily flow out to a creek or something else. Is there a theory behind how often the models need to be updated? That definitely, I would say probably every, I mean, if money were no object and you were doing it, you would just update it almost dynamically as you got projects in, and as survey came in. And that's kind of the way that Hampton Roads Sanitation District does theirs, is that they have two people that are dedicated to those models, and when they get a permit request, they go into that model and they change the basics of it. And if you're doing master planning, I would think that it's probably a lot slower than that. I would say that reasonably 10 years or so, because some basins are not changing very quickly. If you got an area that is growing like, I don't know, Murfreesboro or Franklin, where you have these huge developments going in, maybe more frequent, but you know, downtown Memphis, the elements within that are not changing very quickly. And then, so there is something, and this is again for sanitary sewers, but we worked with the city of Franklin to build this capacity analysis tool where they had a swim model that was used for their sanitary sewers. And if they did get a capacity request for 130 condos or something like that, they could type that in. They say 130 condos is going in to this manhole, and it would run the model with that extra flow super quickly, and then generate a profile. How full is that pipe getting? And in theory, they would take that information and say, you do or you don't get a permit because we're 90% full on this pipe, or you do get a permit, but we require this compensatory upgrade of this pipe, or you need to, your yard pipe needs to go somewhere else. You know, we're a lot of this stuff is catch up. It's stuff that's going in already that they're backlogging in, but you can do that sort of thing with stormwater modeling as well. If HEC-RAS is used in a karst basin, how likely is it to be accurate? Oh gosh, that's a really tough one. I wish I knew more about HEC-RAS to tell you that, because you know, when you're looking at that floodplain, you know, a karst basin, you have this massively distributed sponge of recharge or discharge into the low portions of the river, and unless the person designing it was really intimate with that style of bedrock, I don't know that it would be that interesting, because typically when we build a model, we go by sort of broad generalizations about the soils. You know, you have type A, B, C, or D, or you know, B, D, what have you, and those tell you something about how quickly water flows through it. You know, what the saturated conductivity is. sand, obviously flow rips right through sand, but a silty clay, most of it runs off or it gets saturated quickly or stays saturated for a long time. But that's just the topsoil, that's not the fractured media underneath it, like a karst basin would have. So I'm not certain that unless there's been something very specific done to a HEC-RAS model that it would be particularly accurate. That's a good question. I don't know that I've ever encountered that. Good topic for second session.
Anything else?
Charlene, you got any others?
No other questions. If you can quit sharing your screen, I will put up our next events going on here. Oh, what happened?
Yeah, I really appreciate y'all hanging in with me. That was a machine gun of information for sure.
Oh, I think that was fantastic. Absolutely. And we had about 43 folks attend. A few folks had to leave early, but it was really good attendance today. I think it was the best we've had so far. So thank you so much, Aaron. That was
Yeah, you're
really
welcome.
appreciated.
And I think I'm going to be giving a tweaked version of this, or hopefully, assuming my abstract is accepted for the conference. I want to fixate this more on the Memphis work we're doing, which will be a lot further along in November. But I think that knowing what I talked about today and what people's questions are, that'll really help me tweak it.
Fantastic. Well, here we have our upcoming TNSA talks. I have listed here on your screen.